Good afternoon, student. Here again, I am Dr. Biswajit Kain from Department of Chemistry, Dr. Sudhit Chandrasoor, Degree Engineering College. Today, I decide to discuss the most important part of quantum chemistry or quantum mechanics, that is Schrodinger wave equation. Schrodinger wave equation play an important role in overall quantum mechanics because the solution of the Schrodinger equation for a particular system or particular problem provides some solution, and that solution become wave function, and from that function or that wave function we can say lots of things about the system or about the problem which we consider for our study. So let's student, here some of the point. In 1925, Erwin Schrödinger developed quantum mechanical wave equation on the basis of de Broglie principle and Heisenberg uncertainty principle. I said it earlier that de Broglie principle and Heisenberg principle are the base of the quantum mechanics. So here scientist Erwin Schrödinger developed a quantum mechanical equation which again on based on de Broglie hypothesis and Heisenberg uncertainty principle. Here I am not going to the details of the derivation or development of the Schrödinger equation, but I want to introduce some point on Schrödinger equation. Here this thing, that is H bar, is the Hamiltonian operator, and this is, that is this function, again I am zooming it, that is H cross is equal to 1 by 2m minus I H cross d dx square plus minus I H cross d dy square minus I H cross d dz square plus the potential function part. So ultimately the equation becomes H cross equal to minus H cross square by 2m delta square plus potential energy. So here delta square, that is this term, is basically called Laplacian operator. which is nothing. It is the d2 dx2 plus d2 dy2 d2 dz2, and this is the Laplacian operator in Cartesian coordinate along the z, x, y and z axis, or basically in 3D, 3-dimensional. Here d2 psi dx2 is the partial differentiation of psi with respect to x when y and z remain constant. So if we apply the Hamiltonian operator on a particular psi or wave function, then it produce or it provide E psi, that is the regeneration of the function, and multiplied by E. Here E is the energy. Very important thing, and you remember, student, when we apply the Hamiltonian operator on a function, it always produce a energy, and it is called eigenvalue. Clear? Now in this equation, with respect to all, the mass of an electron m, and when function is act on that or electron like particle, that is Hamiltonian operator, the wave function psi, it gives back the function psi and multiplied by a constant which is the quantity E, and it is called eigenvalue, and here it is energy, and corresponding function psi is called eigenfunction. So we can say there is a final Schrödinger equation H cross psi is equal to E psi, or simply we can write the Hamiltonian operator H cross psi 2 pi delta square plus potential energy. So if we apply this thing on a particular wave function, then it becomes delta 2 psi plus 8 pi square m h square within first bracket E minus V, that is energy and potential energy, total energy and potential energy, psi equal to 0. So this is the final form of the Schrödinger equation. This form of the Schrödinger equation is time independent Schrödinger equation. So here we are not considering the time, so that's why it is called the time independent Schrödinger equation. So in some cases or some complicated cases, we also can consider the time as a function. We can incorporate in this equation and become more complex, and in that case it is called time dependent Schrödinger equation. But we are not going to that. We want to solve the solution very simply and easily, so we are not making the complex by taking time dependent Schrödinger equation. So here is the derivation of the Schrödinger wave equation, or better you can say proof of Schrödinger wave equation. So here we considering the wave function psi x as a sine 2 pi x lambda. You know all the parameter, that is lambda is the wavelength of the wave function, a is the constant, and 2 pi x, x is the amplitude along the x-axis. So ultimately we will get the final form of the Schrödinger equation, that is delta 2 psi plus 8 pi square m h square within first bracket E minus B psi 0. which we already discussed, and this is the picture of the great scientist Erwin Schrödinger. It's a very important person and develop a new era of the science, or a new platform of the science, which is quantum mechanics, quantum physics, or quantum chemistry. Now, that is the importance, that is the interpretation of the wave function. Here, if we see the Schrödinger equation, we very simply see that it is a second order equation, differential equation. So after solving this equation, we can get a number of solution, but among these solution, some of the solution have the real value or a particular energy value, and that values are called eigenvalues, and the corresponding function are called eigenfunction. So clear? So as it is a second order differential, so we can get a number of the solution, but among this solution, few of the solution have its real value or the particular energy value, and in that case the energy value is called eigenvalue, and the corresponding function is called eigenfunction. So here the psi wave function is a function of in Cartesian coordinate x, y, z. Here, though it is t is present, but we are not considering t because we are considering the time independent Schrödinger equation. So very simply I am repeating again, minus h cos square 2m delta square psi plus potential energy psi is equal to E psi. So that E is equal to energy value. So we have to find out this E and psi, because if I know the E, then we can say about the energy of the particle or the wave function, and if I solve the psi, then we can say lots of things about the wave function. Now the significance of the wave function. So what kind of information we can get from psi? Very simply, it is a solution of the Schrödinger equation. It represents the amplitude of an electron wave. So how long it is move. Again, it describe the variation of the amplitude of an electron wave with the distance and the direction. Obviously, so when a particle or the electron like particle move, so its distance and the direction varies. Among a number of values, there are only few are acceptable and known as eigenfunction. I said earlier that is among the different solution, some of the solution are acceptable. Here it is acceptable means some criteria, and I will discuss it after this slide. That is, some of the solution are acceptable and it have some condition, and that function are called eigenfunction. Now each eigenfunction correspond to atomic orbital. Again, listen very carefully. Each eigenfunction is obtained from a second order differential equation or Schrödinger equation, provide an atomic orbital in case of atom and molecular orbital in case of molecule. So defined wave function obtained from the Schrödinger equation produce different atomic orbital or molecular orbital. Now, for the condition to be an acceptable wave function, so here these are the point or criteria when a function should be acceptable, or its corresponding energy value would be real value and eigenvalue. Better it is eigenvalue. So what are the condition? Psi must be single valued, because if it is a real, so it should be single value with respect to the its spreading or it moving or distance. Number 2, psi must be continuous, because if it is a real, then the value should be continuous, because if I going through x-axis and somewhere we are not finding the particle, so it is not the real particle. So if I go along the x-axis, then it should be continuous. So function psi will be 0 if r is equal to infinite. So if it is it is a very high value or unacceptable value, then psi will 0, but when r is equal to real, then psi should be real. Now the fourth one, psi should not be infinite over a finite region. So it is just opposite, that is, for acceptable value of x or within the limit, psi cannot be infinite. It is just opposite of 2, that is condition of 2. Now the final thing, that is psi will be unacceptable if slope is discontinuous, that is d psi dx must be continuous function of x direction. So again I am saying psi will be acceptable if the slope is discontinuous. So this basically it is saying that the first order derivative of the function should be continuous. Clear? So these are the criteria for a function to be acceptable. And the last one, if function meet the condition of the above, then the last thing, that is the probability of finding of electron over all the space from plus infinity to minus infinity, that is the integration minus infinity to plus infinity psi square, that is over the region dx dy dz is equal to 1. So it means this integration part or integration equation represent that the total probability of finding of a particle is always 1, and it is plus infinity to the minus infinity. Now the significance of psi. Psi have not now have the particular significance, but psi square have a particular significance. Psi square is related to the probability of finding a particle in a definite value of energy within a certain space or domain or area. For 1D, that is, it is the space between x and x plus dx, that is within a small range. For 3D, it is the volume, that is dV. In case of the electron, the value of the psi square at any point around the nucleus gives a measure of electronic charge density. So psi square is basically represent the density of the electronic function at a particular point. Now if we multiplied the psi square or the density with volume, then we can get the probability of finding of the electron in a particular region. So that is psi square dV is equal to the probability of finding of the particle in a particular volume, that is very small volume, that is delta V. So student, these are the about the very preliminary thing of the Schrodinger equation and the Hamiltonian operator, Laplacian operator, wave function and its significance and its importance, and acceptable value of psi, eigenfunction, eigenvalue, and the condition to be a function be eigenfunction or acceptable function, and the probability concept, and the concept of the orbital, and the finding of the particle of electron in a particular volume. So here I discuss about all of the thing, and in the next slide I will discuss about the radial probability function for a particular orbital, especially for s orbital, p orbital, and d orbital, and lots of things. That is, we will also discuss about the Bohr radius, and we also observed that the Bohr predicted radius is more or less same, which is obtained from the solution of the Schrodinger wave equation. Thank you for your kind attention, and thank you for going through this video class. Student, I have request, if you have any question, you freely ask me and reach to me in my given email address and in WhatsApp and other address given for the communication. Thank you student.